Welcome back, everyone. Professor Rhett Smith for ProtonGuru.com, going over lesson 6.15 in the Organic Chemistry 2 primer today. And we're going to divert from our discussion of how nucleophiles react with carbonyls to talk a little bit about the acid-base chemistry of carbonyl species. If you think about a carbonyl species and the two potential tautomeric forms of this, you can think about this as being in the enol form shown on the right, or the keto form shown on the left. And when you think about this process, which we've already learned about, you see that one of the hydrogens is taken off of the position next to the carbonyl when you go from the keto to the enol form, right? The enol has 2 hydrogens there. The keto form has 3. So there is some reactivity of that site by moving a proton. And the site beside the carbonyl is called the alpha position. Now this site can be deprotonated if we take a base. Whether you think of the species in the enol form, like this, or the keto form, let's use B- for my base, I can think about making the conjugate base of this species. If I draw it being deprotonated from the keto form, I take one of the H's off the alpha carbon, and that's actually a resonance contributor to the deprotonated enol. We draw the enol like this, right? We can interconvert those two resonance structures by drawing arrows like this. And when you deprotonate an enol or a keto form and get these two forms like this, you have what is known as an enolate, which has a resonance hybrid structure, looks like this, with partial negative charge on both the oxygen and the alpha carbon that you deprotonated. And if you're thinking ahead about what we can potentially use these enolates to accomplish, we have a partial negative charge on a carbon. We could start to think about using that negatively charged species as a nucleophile to attack something else that's reactive with a nucleophile, whether that's a carbonyl or simply using this enolate as a nucleophile in an SN2 reaction. So that's kind of where we're going with this. But let's talk about a couple special cases for enolates before we do all that. The first thing I want to point out is that if I have a compound that has several different sites that we could call alpha sites, right? Alpha is just the site right beside the carbonyl carbon. So beside this site or beside this site, all could be called alpha sites. Well, if I have a site that's sort of alpha to 2 different carbonyls, that's going to be more easily deprotonated when I add a base, because the conjugate base anion that we would get has the potential to be resonance delocalized onto that oxygen and to that oxygen in 2 different resonance contributors. So we have a very, very stable case when we have sort of what we can think of as a doubly alpha position between 2 carbonyls. And even if we think about the enol and keto forms of some relatively simple looking species, let's look at the enol form of this, right? To make the enol form, you take one of the H's off of the alpha position. So thinking about this, move it up to this, put the double bond here, we would get this species. And remember, the enol-keto tautomerization is an equilibrium process. These aren't resonance contributors of each other because we've changed some sigma bonding. Now usually the keto form, right, this one over here is the keto form. Usually the keto form is more stable. But in lesson 4.4 we learned about this special super stabilizing effect called aromaticity. Here we happen to have an enol, there's an alkene and an alcohol in the same carbon. We happen to have an enol that is aromatic. So if we're drawing these arrows to indicate which side is favored, the aromatic side is actually favored. So the point of this slide is, in thinking about these type of species or any species, consider all the influences, consider pi conjugation, resonance stabilization, and aromaticity when you're evaluating all these different species. I also want to point out that not every carbonyl functional group is as easy to deprotonate to make an enolate as others. So just to give you a relatively simple example, let's consider deprotonating acetone, which is an example of a ketone, versus ethyl acetate, an example of an ester. Well, if I deprotonate this acetone at its alpha carbon, we would have a species that looks like this. Now, if I think about that versus deprotonating the ester, I've already drawn out the negatively charged carbon. both of them have the potential for resonance stabilization. I've already typed it out, drawn it out with a computer program below. I'll draw it in here for the ketone. They both have two resonance contributors to help stabilize that negative charge by resonance delocalization. The thing is that you have these lone pairs on the O's in esters. And remember from your valence shell electron pair repulsion theory, Vesper theory, that non-bonding pairs, lone pairs, take up more room than bonding pairs. So even if I think, well, there are also bonding pairs to these H's, well, pairs on the oxygen are much larger, and they'll then repel the nearby negative charge on this oxygen and their lone pairs quite a bit. That steric repulsion means that it's more difficult to form the enolate from an ester than from a ketone. That's not to say it's impossible. I just might need a stronger base to make the less favorable enolate from the ester. All right, so with some of those introductory things about enolates in mind, let's think about what we can use these for. Let's say we take a ketone and it has H's on an alpha carbon, and we want to do a reaction. Well, the first step is going to be to add a base. Here we add a very bulky species that's ionic. It will make the T-butoxide anion that we've learned about way back when we talked about E2 reactions, for example. This is a really strong base. So the first thing we'll do is deprotonate this ketone at the alpha position. So after step 1, we will have the enolate. Now step 2, we have this alkyl bromide. I'm going to draw that in here in box A. Well, what we've done in step 1 is taken the base and deprotonated a species to make what is now a nucleophile. So we have this nucleophile, and we have something with the leaving group. We're going to do an SN2 reaction. This will lead to the species shown here, having a bond from this carbon, which was the alpha carbon, and we have 1, 2, 3 carbons in a chain, 1, 2, 3 carbons in a chain that came from this propyl bromide, or 1-bromopropane. So attach to that. And this is our product, a ketone with an extended chain. And I just want to point out here, maybe something to write in the notes part of the page, this isn't the first time we've had to make our own nucleophile and then use it in a second step. We now know several reactions where you have to take a base to make a nucleophile before it does an SN2 reaction. Let me show you a few examples from prior lessons. The first instance where we use this strategy of using a base to make our nucleophile and then doing a nucleophilic reaction, I think came way back in lesson 3.16 when we discussed that a base could be used to deprotonate a terminal alkyne by taking away the most acidic proton and then using that as the nucleophile in an SN2 reaction. So that as a net result, you would get the new internal alkyne from the terminal alkyne you started with. In lesson 6.8, we learned the Wittig reaction, which starts by making a phosphonium salt and then using butyllithium as the base to take off one of the 3 H's, in this case here, one of the H's adjacent to the positively charged phosphorus. And the first step of the Wittig reaction is to do the nucleophilic addition to that carbonyl. In lesson 6.12, we talked about the Gabriel synthesis. And the first step of the Gabriel synthesis is using a base to deprotonate this nitrogen. And then the second step is to use that as the nucleophile to do the SN2 reaction. Here we're doing a very similar thing. We're finding the most acidic proton in this species by adding the base. In this case, it's the alpha site to make the resonance stabilized conjugate base. And then you can do the SN2 reaction. And this is the alpha-Alkylation we're talking about in this lesson. Importantly, the formation of the enolate is the first step. So you can think about this enolate being drawn in either this way, like we've been doing, or in the other resonance contributor where you have pushed the charge up to the oxygen. Now you will see people draw mechanisms where you use this resonance contributor as well. And I remind you about the other resonance contributor because you will often see the nucleophilic attack drawn out in this way instead of how I showed it on the previous page. Right, on the previous page I drew this resonance contributor doing the nucleophilic attack on the bromide. And what this arrow pushing represents is making a new carbon-carbon bond from here to here and breaking this bond to the bromine so that in the end you've added the carbonyl alpha carbon to the carbon with the leaving group. Now this resonance contributor is actually what they call a higher quality resonance contributor than this one, because if you have a choice between a minus charge on a carbon and an O, this is probably a nicer way to represent the structure in terms of stability of where the minus charge would be higher. So you'll see people draw out the enolate like this a lot of times, and then they'll draw the pi bond being the pair that attacks this carbon, again representing a bond formation here with a tendon formation of the OC double bond. So either way you draw it, you'll have this piece. Here's the alpha carbon, which we have here or here. Here's our little piece that's shown in red in our alkyl bromide, and we have attacked this carbon. It's kind of a strange way to draw it out, so once you figure out what the connectivity is from an arrow pushing mechanism, generally you would redraw it in sort of a more traditional looking line bond structure with 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6 carbons, and you get this ketone, which is 2-hexanone.